So back in the early 2000s, IBM and some other people came up with this idea of autonomic computing. At least that's what they called it. And the basic idea is that the hardware and the operating system should detect problems for you and fix them when it can, okay? And there's been a fair amount of progress since then in memory in particular. For example, chip kill DIMMs have an extra DRAM device on them that will take over for failed DRAM. They route the bits from a particular DRAM chip in a special way so that if a DRAM chip fails, it doesn't take out a whole word, it's just one bit in a word, so the ECC can fix things. We now have background patrol scrub to detect single bit errors, fix them automatically, you don't have to do anything. The Linux kernel, when it's notified that a DRAM is having problems, will offline the pages containing the suspect bits. So a lot of things have happened in the memory area. There are other things where less has happened, and also just for history, autonomic computing used to include, well, does include other things, self-configuration, self-optimization, self-protection. But the part I'm interested in, for the prologue anyhow, is detecting problems and correcting them when possible. Okay, so sort of a quick introduction to the NAS environment, the one I have to work with. So the NAS facility at NASA Ames Research Center is part of NASA's Exploration Technology Directorate. And we are the primary supercomputing site for the other NASA directorates. Okay, and there are a few special projects, blah, blah. This results in about 600 project accounts and about 1,500 users. Okay, which is small by some of your guys' counts, surprised me. Okay. These systems include Pleiades, which is an SGI ICE-X cluster, dual InfiniBand fabrics, about 11,000 nodes, each running a PBS MOM. We have 4 generations of Xeon chips out there because we buy it and expand it over time. So we have Westmere, Sandy Bridge, Ivy Bridge, Haswell. We also have 128 nodes with GPU cards, 2 different generations because we add over time. There are 32 nodes with Intel mic cards. And among those nodes out there, some of them have extra memory. So we have kind of a mixture of things that we have to watch out. In addition to those, we have a Hyperwall visualization subcluster of about 130 nodes with GPU cards, but with attached displays. Okay. And then we have a couple UV2000 systems. One of them with 1024 cores and 4 terabytes of memory, and then another one half that big. Okay. Also, sort of on the we have several shared NFS servers for home directories and a scratch file system for I/O patterns that don't fit well with Lustre. We have several Lustre file systems. Those are all connected over InfiniBand. We have a hierarchical file system for archival storage. We have a pool of login hosts where people log in with a load balancer to plop them on a relatively idle login host. We have our baby cluster of recycled off-maintenance nodes that were taken out of Pleiades, and it's got 1,100 nodes, they're all Westmere, and it has a wide area InfiniBand connection to Pleiades file systems, not to Pleiades itself, but to the file systems. And then among all those things, we have 4 PBS servers to manage the mess. Okay. So going down to specifics of our prologue and epilogue are combined into one Perl script. We use the same script across all of our systems, but we have a directory in the PBS directory that has flag files to enable or disable or tune particular features. And normal PBS, pre-version 13 anyhow, I'm not exactly sure what 13 does yet. The Prologue was run only on the first node in a job. So our version, the Prologue would run on the first node, and if it was successful, it would then farm out to all the other nodes in the job using PDish or Dish or SSH, whatever was available, to run itself on the other nodes. The epilogue always runs on all nodes. In our case, it runs on the first node, and then it always goes out, whether it's successful or not, to the other nodes. And then to reduce the server load, when a 1,000-node job starts up, you don't want all of the nodes talking to the server, asking, tell me about the job. So instead, we leverage the fact that the first node's mom has pushed the job information to all of the other nodes, and we just read that file to gather information. So we use print job against the job file on the remote nodes to get the information we need. Okay. So that's kind of how we run the prologue and epilogue. And its job, in our case, is to build a sane environment that stands a good chance of running the job the way the job wants to be run. So that's what it's supposed to do. Except on the UV systems, we pretty much, all of the jobs are run with exclusive access to their nodes. We have very, very few jobs that are willing to share nodes with other jobs. In fact, I'm probably the only person who submits them just for testing. Okay. And that means that the prologue can tune a node to a specific job. Okay, if there are features of the node that make more sense one way or the other, the prologue can do that. And so some of the examples of what our prologue does on AIX power, which we don't have anymore, but the code's still there. We can enable or disable SMT, which is hyperthreading. And that, we can actually do that currently on the ICE systems, but we haven't found a lot of difference in performance with hyperthreading on or off. But on the power, it made more difference. So on our GPU nodes, for security reasons, we set ACLs on the NVIDIA special device files so that only the ID running on the node has access to the NVIDIA device. On our mic nodes, the prologue goes out and checks to make sure the mics are actually running, just sort of make sure they're there. And then we have 2 sets of home file systems. On the archive servers, okay, they have 1 set of home file systems because those are the hierarchical file system. You put your file in a home directory and it goes off to tape. Okay, but on Pleiades and everything else, it's a standard, the NFS file system. So we have 2 sets of them. We have some nodes that have large memory and are connected both to the cluster file systems and to the archive file systems. And when the job runs on one of those nodes, it can run thinking it's either a data analysis node associated with the archive system, or it's just a large memory head node for a cluster job. And so we have to point the home directory to the right set of file system at the start of the job. And we do that through a /u symlink that we change according to the job. Okay, so that's kind of the tuning part. And then here's the part about making sure the job will actually be able to run on the node. So when the job starts, the Prologue goes out and checks that the user has a home directory and a scratch file space available, okay? Sometimes users kind of jump the gun and run jobs before their home directory is set up or before their scratch file space has been set up. Sometimes the file system isn't there, and so you have to check for those things. If it's not there, we requeue the job and hope it tries again and gets a different set of nodes. Bad things happen if the clocks on the nodes are different from the clocks on the NFS servers. So the Prologue checks that NTP is running and is synchronized. We use SGI's MPT as our primary MPI. And MPT uses array services daemon to handle remote starting processes on remote nodes. And the Prologue checks that array services is running and responsive. If it's not, the Prologue tries to restart it. Okay, that's part of the automatically fix things technique. And if it's unable to restart it, then it gives up, offlines the node, requeues the job. And then our systems primarily are ISEX, which are diskless, and they their writable disk space is a small allocation on a rack leader node, and that allocation is used for /var, among other things, and var can fill up for various reasons. So we check the amount of free space on var, and if there's not enough free space, we requeue the job and offline the node. Okay, so it has to try again. Okay, memory. So, like I said, there's been a lot of progress in the hardware side of memory, but memory also has issues that we have to detect from the software side. So one of the things that our Prologue does is it cleans up stray user IPC shared memory segments. So we sort of tell users, promise users that they get, when their job starts, they'll have, I think it's like 85% is what we claim, of the physical memory on the node will be available to your job. Okay, well, we need to make sure that's true. So this is what we're doing. We're cleaning up things that might have occupied some memory that will cause this job to run out of memory. So clean them up. The IPC shared segments, we should clean up dev.shm, but we currently don't. We'll do it later. So again, that part we can do only because we're running exclusive access to the node. You can't do a lot of these things if you're sharing the node because you're kind of wiping out some stuff that another job might be using. But this one's okay since we're running exclusive access. We flush various I/O caches. We do a sync. We do an L flush so that Lustre frees up any locks it has. There's nothing running on the node now, so there's no point to having any locks. Free them up. And then we do tell the kernel to drop caches, again, free up memory. On the shared hosts, which currently is normally only the UV systems, but like I said, you can run shared jobs. We run BC free instead to free up the buffer cache, which is less thorough, but it's what we can do. It's safe. On our diskless nodes, temp is a RAM-FS, so it lives in memory. So the previous user might have used a lot of temp for junk. So we clean that up simply by unmounting and remounting it. Poof, all clean, all empty, real easy. If we can't unmount it for various reasons, we offline the node, requeue the job. And then when all of that's done, we check that at least a certain percentage of the physical memory is now available, is free. Okay, and if it's not, reissue a message, requeue the job. Okay, now the next thing, the stream, okay, this isn't in the prologue, it's an end of job hook, but we also run the stream benchmark when the job's finished. And stream benchmark is really good at finding nodes that are having problems with correctable errors that have somehow got memory tied up so that you're getting a lot of cross-socket memory references because the first socket has too much memory tied up. And it also occasionally finds some other CPU issues. It finds locked processes, kernel processes that are spinning. So it's actually a pretty good test. We run that for a very short time at the end of job. If there's a problem, we offline the node, and that's at the end of the job. Okay. So that gave us a nice clean environment. The job stands a chance of running. Maybe. Okay, so in the epilogue, we have to undo or clean up some of the stuff that we did in the prologue. So, oh, did I miss that? I did miss that, sorry. Is it back here? Last one, the bullet, last one. Okay, on our UV2000s, we use CPU sets to confine jobs to particular sets of memory and particular CPUs. But the CPU sets created by PBS are owned by root. The user can't do anything with them. But CPU sets contain some tuning parameters related to how buffer I/O is done where particular users' jobs might prefer one set of tuning versus another set of tuning. So what we do when we start a job on a UV2000 or a CPU set system is we create a CPU set inside the PBS CPU set that's writable by the user. Okay? This CPU set allows the user to tune various buffer parameters but it doesn't allow him to escape the CPU set that PBS created for it. So when the job ends, we have to get rid of that special CPU set before PBS cleans up the outer CPU set. Let's see, as I said, okay, on the GPU nodes, we kill off X, again for security reasons. We undo our special ACLs on the NVIDIA special files so that nobody has access to the NVIDIA device anymore. Let's see. On the mics, we reboot the mics because the current mic software state is still not all that good. And it's really easy for users' jobs to hang up the mics. And just to make sure things are going to be nice for the next job, we just reboot them. Okay. So the epilogue, again, because we're assuming exclusive access to the nodes, kills off any stray processes belonging to the user. Now the mom is also configured to do the same thing, but we do it twice. No, they get slightly different things. Our mom has a local mod though, that if the standard mom process to kill off stray processes doesn't work. It tries to kill the process doesn't go away, it tries again, process doesn't go away, etc. Then the mom, after a certain number of retries, or I forget, it's retries probably, gives up. The mom simply goes away. Okay? This causes PBS to claim the node is down. Okay, eventually this comes to the attention of the operators, okay, and unfortunately this is still manual. Comes to the attention of the operators who figure out why this process didn't go away, and typically the result is to reboot the node. Right? It makes them go away. Okay, so in this case, the mom going away just leaves the node down. We could offline the node, but since the typical response is going to be to reboot the node, when the node comes back up, PBS is going to restart the mom starts up, the node's no longer down, it's now up, and the state has been cleared without any additional operation. If we offlined it, we'd have to online it. So by having it down instead, we do kind of make it easier to bring it back into production. Okay. Then our epilogue has some, so Pleiades is a big system, 11,000 nodes, and you don't idle the whole thing out if you want to do something to all of the nodes. Instead, you want to do things as jobs finish. When the nodes free up at the end of a job, you can do something. You can reboot the node if you need to switch to a new image. You can, well, there are other reasons for rebooting the node. And so the epilogue detects if we want something special to happen between jobs. Okay, and if we want something special to happen, the epilogue calls this helper called cycle nodes to do the special stuff. Okay, and then the epilogue goes on, finishes up its other stuff. So we'll get to cycle nodes in a minute. Okay, the other thing, our prologue and epilogue are responsible for is some reporting. Reporting's important. So our prologue puts this kind of header in the job's output. Okay, we've got the job name, when it started, what kind of resources it requested. We have PBS set certain environment variables, so it lists the ones that it put in the job different from what the user might have specified. And then we indicate which first node the job's running on. So this output is important because it allows our user services people to look at the output and immediately know which job it is, so we can go and get the other information for the job, when it ran, so important information about the job. We don't have to rely on the user's memory about what this job did. The user doesn't have to rely on his memory about what he was doing in this job. So we stuff that in the beginning of the job output. Then, when the job ends, because Lustre is kind of important for most of our jobs, we print some Lustre file system usage statistics. So we print out metadata operations, how many opens, how many closes, how many statfs's, the total number of bytes read, written, and then I/O transfer sizes in various buckets. 4K, bad, megabyte, good. So that we can look at that and inform the user that they're not doing very efficient I/O or whatever. And in addition to reporting this in the user's output, we also syslog this data in a condensed form so that we can analyze the syslogs and see what kind of I/O is actually being presented to our Lustre file systems. Okay. Then additional information that comes out after that is resource usage summary. Again, we've got the job ID there, so we know which job, when it finished, how long it took, what billing information is associated with it, which queue it ran in. Useful stuff there. And again, mostly this is for the benefit of the user services people helping the users so we know what the job did. Exit code, not that that's useful for anything, really. Okay, so that's the prologue and the epilogue, but they have, one other step. So there's a question. Where do you do this stuff? Do you do it in the prologue? Do you do it in the epilogue? Do you do it via hooks? And if you do it in the prologue, they take time. these particular checks take time. If you do it in the prologue, the user notices a pause between the time they do the Q sub minus I and the time they can actually type something. On our systems, with what we have in the prologue, that's currently several seconds. You notice it, okay? You could do it in the epilogue. A lot of the stuff you could do in the epilogue, for the health checks anyhow, but that means that the health status is from the previous job, when the previous job ended. It doesn't tell you what the state of the node is now. So it's not quite so good to do these in the epilogue where the user wouldn't notice them so much. And you could do them via hooks, except, this is probably better now, but except you have less control and there's probably more overhead for doing all this stuff from hooks than doing it from Perl in one script. So we use the prologue for most of our checks. Okay. It can't do this on its own, prologue and epilogue, so we have some helpers. The PBS startup script itself we modified, and first, we know how much memory is supposed to be in each node. So the startup script checks that there's that much physical memory available. If it's not there, it never starts the mom, the node stays down, we look at it eventually. The startup script checks that all of the required file systems are mounted. If they're not mounted, it tries to mount them for quite a long time. It turns out that when a lot of nodes reboot at once, our NFS servers can't keep up with the mounts, and so quite often, about half of the nodes rebooting, if you reboot 500, 1,000 nodes, don't have the NFS file systems mounted. So the startup script goes out there and gets those file systems mounted by patiently waiting, trying again. And then the startup script also invokes cycle nodes, which we'll get to in a moment, and telling it, hey, I'm back up. Okay, cycle nodes is this guy responsible for doing things between jobs. And it runs independently of the epilogue, so the epilogue can complete its processing, the mom can get rid of the job, clean everything up nicely, and then cycle nodes does its thing. You can't do it in the epilogue because if you reboot the node in the middle of the epilogue, it's not going to be nice. Okay. So when it's called from the epilogue, the first thing it does is it makes the node unschedulable. We use a special node attribute for that, a local node attribute. So we don't have to offline the node, we just change a value that means that the scheduler looks for, and the value's wrong, it won't schedule anything to the node. Okay. Then it hangs around waiting for job processing to complete, files to stage out, all that good stuff. Then eventually it performs the between job function. Okay, and then when called from the prologue, it marks the nodes for use again. So the sorts of things we use this for, as I said, just rebooting nodes between jobs. If we want to switch all the nodes to a different image, okay, we set them all up to run the new image, configure them to boot into the new image, and then use cycle nodes so that the next time a job ends, they'll boot into a new image. If we need to restart a particular server between jobs, for example, if you want to restart the mom, okay, it works better if you do that when there are no jobs on the node, so you can configure it, okay, restart the mom. The array services daemon I mentioned that helps out the MPI, you don't want to restart that while jobs are running. So again, there are things you can do safely between jobs that you can't do while jobs are running. So that's what cycle nodes takes care of. Okay, then this wonderful tool that makes a lot of things cleaner is SEC, the Simple Event Correlator. Okay, so SEC, in our case, watches the console logs and the syslogs of all the nodes. All right? It detects certain patterns of messages and takes actions based on those patterns, those messages. Okay? In our case, among other things we have, so it watches for messages from the prologue and the epilogue so they can keep track of which job is running on the node. Okay, so now SEC knows which job is running on a particular node. Then the sorts of things SEC does for us. Okay, when a job runs a node out of memory, the kernel killer reboots the node. Okay, it puts out some messages first, but it reboots the node. Okay, SEC detects the message from the kernel about that and QDELs the job. There's no point running that job again, which would be the normal course of action if a node reboots out from underneath it, because it's going to do the same thing again. It's going to run the node out of memory again and again. So don't do that. We QDEL the job, and then we send mail to the user explaining what happened to the job. Now, because SEC is an event correlator, okay, it sees that 20 of the nodes in a job oomed. That's typical, okay? And it sends only one email. The user doesn't get one from every node that ooms. Okay, so that's really nice feature of SEC. Okay, SEC watches for the memlog predicted DIMM failure messages. And when it sees that, even though the node is still running, it marks it as unavailable for future scheduling. Okay, so nobody else is going to get assigned to that node, but we'll go ahead and let the current job run. We have another script that looks for those same messages once a day and is used to generate tickets to the engineers to replace the DIMMs. Okay, and SEC also watches for the hard ECC errors and offlines the node in that case. Okay. If the prologue reports that nodes were low on memory, it offlines the nodes. Again, prevent new jobs from running there. SEC also detects where the PBS mom starts multiple times without an intervening stop, and that probably means the node has spontaneously rebooted for some reason, either because it's got a hardware problem, or it just feels like it, or because the operators had to reset it because it locked up. And if we see 2 of those startups in a 12-hour period, then we mark the node offline. There's something wrong with it. Okay. Then another feature of SEC, or another use we have for it, is that the kernel, okay, if a node gets evicted from the Lustre file system when there are dirty pages, data that should have been written to the file system but couldn't make it because the node got kicked out, the kernel issues syslog messages, indicating the user ID and some information about the path to the file that owned the blocks that couldn't get written. So it syslogs those and goes on its way. SEC notices those messages and constructs an email to the users telling him this file might be corrupted, you should check it, and just to let our users know when we have a strong suspicion that one of their files got corrupted due to a Lustre eviction. Okay, so those things were all automatic tools. We have another tool called Diagnose that's a Python script with plug-in architecture where you can plug in little scripts to handle particular small piece of verification. Okay, and each handler has 2 entry points, a check entry point and a fix entry point. Okay, so you go through typically, and Python Diagnose will run the check entry point, and if there's a problem, it'll queue that thing up to be fixed after it's gone through all the checks. Okay, so potentially you can run Diagnose and it'll do things, check things, and fix them. We don't have enough fix scripts yet, but nonetheless. Okay, Diagnose also knows of the dependencies among the checks. Okay, there's no point checking to see if you've got enough memory free if you haven't already checked to see that the caches have been flushed and that the physical memory is present and all that. Okay, so the dependency part is really useful so one example of that is on the rack leaders for ice systems currently. I think it's changing. The rack leader is monitoring the temperatures of the blades, okay? And it's monitoring it through a fairly indirect method that has lots of pieces that can fail. IPMI tool, PCP, PMIE, each one of those can fail in its own way. So the diagnose has a script to go out and check. Can I talk to the blade to find out its temperature? Yes. Oh, okay. Can PCP tell me what the temperature is? Yes. Oops, no. Is PMIE monitoring this stuff to warn us about it? And if something goes wrong, it knows how to restart each of those pieces, what order, and bring it back up so it's working again. So we put that in after an incident where temperatures got really warm in the machine room and nothing happened. Well, nobody told us soon enough. So this guy fixes them so we have current information about the temperatures. Another thing that we have it do is it checks the firmware versions on the InfiniBand cards so that if we have to replace an InfiniBand HCA, diagnose will tell us, oops, you haven't updated the firmware on it yet, you'd better do that. So we run diagnose after maintenance before putting the node back into service. The engineers do that. Okay, that's all the good stuff. So now things that we should do in the future, or thinking we're doing in the future. It would be nice to move a lot of the non-PBS checks and fixes out of the Prologue and epilogue and put them in diagnose. So there's one place that's the knowledge about how things should be. And especially it provides the structure to make it easier to write the fixing parts. We don't fix enough things currently. We detect things, but we don't fix enough that we could. And so putting them in diagnose is kind of the right place for that. And then we'd have the Prologue and the epilogue invoke diagnose. Okay. We currently don't have tests on InfiniBand health, and that's the end. So while we're here, what do you people do for node health or node fixing stuff or node it's broken, tell me about it stuff?
First, thank you.
Okay.
Rather than let you ask questions, you need to answer his question, I think.
Thanks very much, Dale. That was really interesting. On your future plans for InfiniBand health, how are you going to do that from the node? Or RSGI going to provide a solution?
I didn't hear all that, sorry.
Sorry. For the tests on InfiniBand health, do you have any ideas of what you might use? Because I think that's really difficult.
So, okay. What we want to do there initially is just look at the error counters on the node's HCA. There should be no errors. Okay, any error there is a problem in our experience. And so we don't want to use a node whose HCA has generated any errors. Okay, with the appropriate definition of what an error is. There should be no symbol errors, there should be no link drops, there should be no, port receive errors are okay, depending. Okay, and that's what we do on the nodes. We have another process that we use for monitoring the switch-to-switch links in the InfiniBand fabric. Because it's really tricky to go that first jump from the node to anywhere else in the fabric, okay, to find out, is the link I'm connected to seeing errors? Okay, that's actually kind of tricky to do, and we're not planning to do that the first go-round.
Other questions? While I'm looking around, I'm going to ask mine, which is
Oh, come
so
on, you guys
how
do some
often-
health checks. What else do people do?
Yeah, thank you, Dale, for kind of giving us your checklist. I think here at Boeing, we use Bright Cluster Manager to do most of our health checks. They're actually done in the context of the Prologue and epilogue. So we actually check both going in and coming out of a job. Our list actually matches yours pretty closely. We're using UFM. I believe we have some checks that directly talk to UFM to do IB health, but I
Gotcha.
don't really know the nature of the details on that. I certainly want to compare notes with you in the future on some of these things. I think a lot of the checks, it sounds like you've had kind of the same journey we have in terms of we spot a problem, we build another check. And so
Yes.
I will say that Bright has been really good for providing a framework for doing that, and we really have consolidated all our health checks into that tool. So,
Okay.
thanks.
How often do things fail? Like, will you get one node down a day, 10 nodes down a day, 100,000
Okay.
nodes down a day?
We have sort of guesstimates of that. I had one thing where we check on the temperature monitoring, okay, and we have like 100 and some racks, and there will be one failure a day on temperature monitoring where we were no longer able to monitor the temperatures on that rack, which, if you ask me, is way too many. But SGI is working on a different way of doing that monitoring that's probably more reliable. We're not using it yet. DIMMs, 3 or 4 DIMM failures a day. Nodes that spontaneously reboot for unpredictable or unknown reasons, 1 or 2. Failure to unmount temp, maybe 2 or 3 a week. What else do we have? File system issues all the time, it's Luster. Let's see. I think that's about it. Well, yeah, for the ones I remember, those are the ones that show up most often. Unkillable, yeah, the mom going away 2 or 3 a week, maybe? Is that about right, Greg?
It depends on the users that week.
Yeah, it does, yeah. Yeah.
Okay, thank you again.